Hello there, and welcome back to Bedtime Science. I am really glad you are here tonight. Somewhere beyond the solar system, a planet may be passing in front of its star. No eye is close enough to see the crossing. The planet is too small to resolve in ordinary images, the star too bright beside it, and the distance too great. From Earth, the entire system may appear as one point of light among thousands. Yet for a few hours, the planet places a thin atmosphere between its star and our telescopes. Most of the starlight passes through unchanged. A very small part does not. Water vapor may absorb one group of wavelengths. Methane may remove another. Carbon dioxide may leave its own pattern. Clouds may flatten the signal. The star's surface may imitate a planetary feature. Noise in a detector may create a shape that disappears when the observation is repeated. By the time the light reaches us, it carries a question hidden in what is missing. Could anything be alive there? This is how the search has changed. For most of human history, worlds around other stars belong to philosophy, imagination, and theology. No telescope could prove that even one existed. The stars were points without visible companions, and our solar system could be interpreted as a unique arrangement. Today, more than 6,000 planets beyond the Sun have been confirmed. They orbit ordinary stars, dying stars, pairs of stars, and stars much smaller than the Sun. Some complete a year in less than one Earth day. Some are hotter than molten metal. Some move on stretched orbits. Some belong to systems packed so tightly that several could fit inside the orbit of Mercury. Most are not places where life as we know it could survive. A few are small enough, cool enough, or chemically interesting enough to keep the question open. No confirmed biosignature has been detected on an exoplanet. No radio signal has been confirmed as coming from another civilization. No organism has been found beyond Earth. The answer remains unknown. That uncertainty is not an empty space where science has failed. It is an active frontier built from measurements that were impossible within living memory. Tonight, we will follow the frontier slowly. We will begin before the first confirmed exoplanet, when astronomers tried to detect invisible worlds by watching stars move. We will pass through the first planets found around a dead star, the hot Jupiter that overturned planet formation, and the Kepler mission that showed planetary systems to be common. Then we will move from finding planets to asking what those planets are like. We will enter atmospheres through starlight. We will examine the habitable zone and why it is not a guarantee. We will visit red dwarf systems, ocean worlds, false biosignatures, and the difficult case of K218b, where the same spectrum has produced headlines about life and careful papers arguing that the evidence is not there. Eventually, the search will widen from biology to technology. Radio telescopes will listen. Lasers will be considered. Strange stars will be investigated. The silence of the sky will become a scientific fact whose meaning remains uncertain. At the end, we will return to the missing wavelengths in that distant beam of light. The question, are we alone? Sounds like one question. In practice, it contains many. Do planets form commonly? Do rocky planets retain atmospheres? Does liquid water persist? Does chemistry become biology easily? Does simple life become complex? Does intelligence become technology? Does technology remain detectable long enough for two civilizations to overlap in time? Each step has a different kind of evidence. The first step, the existence of other planets, seemed nearly impossible to test. Ancient thinkers imagined plural worlds without instruments capable of deciding the matter. In the 5th century before the Common Era, the atomists Leucippus and Democritus described nature as matter moving through empty space. Later, Epicurus argued that the number of worlds could be unlimited because the universe contained enough atoms and space to form them. These worlds were philosophical consequences, not observed planets. Aristotle offered a different cosmos, one ordered world with Earth near its center, enclosed by celestial spheres. His system shaped European and Middle Eastern thought for centuries, though scholars debated and modified it in many ways. The invention of the telescope did not immediately reveal exoplanets. It changed the scale of possibility. Galileo saw moons orbiting Jupiter, proving that not everything revolved around Earth. He saw phases of Venus, supporting a sun-centered planetary arrangement. The moon had mountains. The sun had spots. The heavens were not a separate realm of perfect, unchanging objects. Johannes Kepler described planetary orbits as ellipses and connected their periods with distance from the sun. Isaac Newton showed that the same gravity pulling objects toward Earth could govern the moon and planets. A planet became a physical object following universal laws. If other stars were suns, perhaps they too could hold worlds. Giordano Bruno is often presented as a martyr for exoplanets because he wrote of innumerable suns and worlds. His execution in 1600 followed a complex religious trial involving many theological positions, not one astronomical claim. The history is more complicated than the popular story. Still, the plurality of worlds had entered European debate. Christian Huygens later imagined planets around other stars in his Cosmotheoros. He reasoned by analogy. The sun is a star, the stars are distant suns, and nature might repeat planetary systems. Analogy could suggest. It could not detect. The first serious searches looked for motion. A planet and star orbit their shared center of mass. The star is much heavier, so its movement is smaller, but it does not remain perfectly fixed. If the system is seen at the right angle, the star moves slightly toward Earth and then away. Light records that motion through the Doppler effect. When the star moves toward us, its spectral lines shift toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. The change can be extremely small. A planet like Jupiter causes the sun to move at roughly 12 meters per second. Earth causes a motion of only about 9 centimeters per second. The 19th century supplied spectroscopy. The 20th supplied stable instruments, electronic detectors, and computers capable of comparing thousands of spectral lines. But false discoveries came first. Astronomers repeatedly announced planets that later disappeared under better analysis. Small errors in a star's measured position could imitate an orbit. Activity on the star could imitate a velocity change. A telescope or spectrograph could drift. Too few observations could make noise resemble a periodic signal. The desire to find another world made caution essential. One of the most famous false cases involved Barnard's star. In the 1960s, astronomer Peter van de Kamp reported tiny changes in the star's motion that he interpreted as planets. The system was nearby, and the claim lasted for years. Other observatories did not confirm it. Later investigation showed that adjustments to the telescope at Sproul Observatory coincided with changes in the measured stellar positions. The planetary signal belonged at least partly to the instrument. Barnard's star eventually did become associated with modern planet candidates and later confirmed planetary evidence, but not through Van de Kamp's original astrometric claim. The episode taught a lesson that would return throughout astrobiology. An exciting pattern is not enough. It must survive different instruments, different analyses, and time. The first confirmed exoplanets arrived from a place almost no one had expected. They did not orbit a star like the Sun. They orbited a pulsar. A pulsar is the dense rotating remnant of a massive star that exploded. It can sweep radio beams through space with extraordinary regularity. Each time the beam crosses Earth, radio telescopes detect a pulse. The pulses act like a cosmic clock. If the pulsar moves because unseen planets pull on it, the arrival times shift slightly. In 1992, Alexander Woolsden and Dale Frail reported planets around the pulsar PS RB 1257+12. The system contained at least 2 planets with masses in the broad terrestrial range, and a third was later established. The first confirmed exoplanet system was built around a stellar corpse. Its planets may have survived the star's transformation, formed from debris after the supernova, or followed a more complex history. They were unlikely homes for surface life as we know it. Yet they proved the central point. Nature makes planets beyond the solar system. 3 years later, the search reached a star resembling the Sun. At the Haute-Provence Observatory in southern France, Michel Mayor and Didier Queloz used a spectrograph called SETI to measure stellar velocities with new precision. They watched the star 51 Pegasi. Its spectrum shifted back and forth every 4.23 days. The signal implied a planet with at least about half the mass of Jupiter orbiting extremely close to the star. The result looked wrong. A Jupiter-like planet should have formed far from the heat, where ice could help build a massive core. At 51 Pegasi B's orbit, a year lasted just over 4 days. The planet was far closer to its star than Mercury is to the Sun. Some astronomers wondered whether the star itself was pulsating. Independent observations confirmed the velocity signal. 51 Pegasi B was real. The first planet known around a Sun-like star was not a second Earth or a second Jupiter in a familiar outer orbit. It was a hot Jupiter, a type of world absent from our solar system. The discovery did more than add one planet. It revealed that the solar system was not a complete template for planetary architecture. Planet formation could move worlds after they formed. A giant planet could exchange angular momentum with the disk of gas around a young star and spiral inward. Gravitational interactions among planets could scatter bodies into new orbits. Tides could later circularize a close path. Migration became part of the standard story. The first discoveries were teaching astronomers not only that planets existed, but that imagination constrained by one planetary system had been too narrow. A new field began with surprise. The discoveries multiplied because astronomers learned to use several kinds of indirect evidence. Radial velocity remained one of the most productive. A spectrograph separates starlight into a spectrum crossed by absorption lines. The lines come from atoms and molecules in the star's atmosphere. Their exact positions shift with motion. The instrument must remain stable while temperature, pressure, and mechanical stress try to change it. A planet may move its star by less than the pace of a person walking. Modern spectrographs are placed in controlled environments and calibrated with lamps, absorption cells, or laser frequency combs. Thousands of spectral lines are compared together. Even then, the star is not quiet. Dark star spots rotate across the surface. Bright magnetic regions appear and disappear. Convective gas rises and falls. Flares alter line shapes. Stellar activity can create a false periodic signal or hide a real one. A planetary period should remain coherent. Activity often changes as spots evolve. Multiple indicators are compared. Observations extend across years. The star must be understood before its movement can be trusted. Radial velocity usually provides a minimum mass rather than the true mass because the orbital inclination may be unknown. If the system is nearly face-on, the star's motion is mostly across the sky rather than toward and away from Earth. The measured Doppler signal then underestimates the companion. Another method can supply the missing angle. A transit occurs when the orbit is aligned so that the planet crosses the face of its star from our perspective. The planet blocks a fraction of the light. A Jupiter-sized planet passing in front of a Sun-like star removes about 1%. An Earth-sized planet removes only about 1 part in 10,000. The dip repeats with the orbital period. Its depth gives the planet size relative to the star. Its shape reveals how the crossing occurs. Repeated changes in transit timing can reveal additional planets pulling on one another. When radial velocity and transit data are combined, astronomers can estimate both mass and radius. From those comes average density. A dense small world may be dominated by rock and metal. A low-density planet may contain a large envelope of hydrogen and helium, extensive water, or an inflated atmosphere. Density narrows the possibilities without supplying a complete interior. Earth and Venus have similar size and bulk composition, yet radically different surfaces. A planet's radius is not its climate. The first known transiting planet around a normal star, HD 209458b, was detected by radial velocity and then seen crossing its star in 1999. Its transit confirmed that hot Jupiters were planets rather than hidden stellar behavior. Soon, astronomers detected sodium in its atmosphere. They watched the planet pass behind its star and measured the loss of infrared light, separating the planet's heat from the combined system. An exoplanet had become more than a mass and orbit. It had temperature and atmosphere. Transits created an opportunity for scale. A single telescope could monitor many stars and wait for repeated dimming. The idea seems simple. It required years of persistence. William Barucki began advocating a space mission to search for Earth-sized transits in the 1980s. Earth's atmosphere makes extremely precise, continuous brightness measurements difficult. Daylight, weather, and the rotation of Earth interrupt observations. A telescope in space could watch one field without those gaps. Several mission proposals were rejected. The technology and expected planet numbers were uncertain. Could detectors remain stable enough? Would enough stars be quiet? Were Earth-sized planets common enough to justify the mission? The project evolved and returned. It became Kepler. Launched in 2009, the Kepler spacecraft stared at a field in the constellations Cygnus and Lyra. It monitored roughly 150,000 stars during its main mission, measuring brightness again and again. Kepler did not fly from star to star. It waited. For a planet like Earth crossing a star like the Sun, one transit occurs each year. At least 3 similar events were often needed to establish a period. The telescope had to remain precise for years before the pattern became visible. Most dips were not planets. Binary stars could eclipse. A faint background binary could blend with a brighter target. Instrument artifacts could imitate transits. Star spots could create changes. Candidates were checked through imaging, spectroscopy, transit shape, statistical validation, and sometimes direct mass measurements. Kepler's strength was not only the number of confirmed worlds. It measured what had been hidden by discovery bias. Radial velocity surveys favored massive planets close to their stars because they produce large, rapid wobbles. Transit surveys also favor close planets because they cross frequently and have a higher probability of alignment. Kepler could still correct statistically for many missed systems. It showed that planets are common. Small planets are common. Compact systems are common. The solar system is one architecture among many. The mission also experienced failure. In 2013, a second reaction stopped working. Kepler could no longer hold its original field with the required stability. The main survey ended. Engineers found another way to balance the spacecraft using pressure from sunlight. The redesigned K2 mission observed a series of fields along the ecliptic. A damaged telescope became useful again. By the time Kepler stopped operating in 2018, it had transformed the question from "Are there other planets?" to "Which kinds of planets are common, and what do those statistics mean for life?" TESS followed with a different strategy. Launched in 2018, the Transiting Exoplanet Survey satellite scans broad regions of the sky, emphasizing bright and nearby stars. Kepler looked deeply at one field. TESS searches most of the sky in sectors. Nearby bright hosts are valuable because other telescopes can measure masses and atmospheres more effectively. TESS has found large numbers of candidates and confirmed planets, including multi-planet systems and small worlds around nearby stars. Ground-based observatories then return to those stars. The discovery becomes a relay among instruments. Some planets do not transit and produce velocity signals too small to detect. Astrometry measures a star's position on the sky and searches for a tiny side-to-side orbit. The principle is old, and the required precision is extreme. The European Space Agency's Gaia mission completed its sky scanning observations in January 2025 after more than a decade of measuring stellar positions across the Milky Way with extraordinary accuracy. Its stored observations and future data releases can reveal massive planets on wider orbits and determine true masses when combined with other methods. Direct imaging attempts the apparently obvious method. Take a picture. The difficulty is contrast. A mature Earth-like planet reflecting visible light can be billions of times fainter than a sun-like star. The two are separated by a tiny angle. A telescope must suppress the starlight while preserving the nearby planetary signal. Coronagraphs block or redirect light inside the instrument. A future star shade could fly separately and cast a precisely shaped shadow over a space telescope. Current direct images usually show young, hot, massive planets far from their stars. These worlds still glow with heat left from formation and stand at wider angular separations. The system HR 8799 contains several directly imaged giant planets. Observations across years show them moving in orbit. Beta Pictoris b has been followed around its young star. Its atmosphere contains clouds and molecules measured through infrared spectra. Direct imaging produces a point of planetary light, not a surface map. Yet that point can carry temperature, chemistry, cloud structure, rotation, and eventually perhaps evidence about climate. Gravitational microlensing searches in another way. Gravity bends light. If a foreground star passes almost exactly in front of a distant background star, the foreground gravity magnifies the background light. A planet around the lens star can produce an additional brief disturbance. The alignment may never repeat. A microlensing planet can be discovered from one event and remain difficult to observe again. The method is sensitive to planets farther from their stars and to systems thousands of light years away, complementing transit and radial velocity surveys. It can also detect planets that wander without stars. Free-floating planets may have been ejected through gravitational encounters or formed through processes resembling small stars. How many exist remains uncertain because the events are rare and short. The Nancy Grace Roman Space Telescope is planned to conduct a major microlensing survey, adding population information for planets at distances from their stars where Kepler was less sensitive. Each method has a selection effect. Transits favor aligned, close systems. Radial velocity favors massive planets, and active stars complicate the signal. Direct imaging favors young, hot, wide planets. Microlensing favors chance alignments and often distant systems. Astrometry favors massive companions in sufficiently wide orbits around nearby stars. The catalog of known planets is not a neutral sample of the galaxy. It is a map shaped by our tools. This matters whenever one class appears common. Hot Jupiters were among the first planets found not because most planets are hot Jupiters, but because hot Jupiters are easy to detect. Their large masses create strong velocity signals. Their short periods repeat quickly. Their large sizes block substantial starlight. As precision improved, the planetary zoo changed. One of the most common categories found by Kepler has no direct counterpart in the solar system. Super-Earths are larger than Earth and smaller than Neptune, though the name describes size or mass rather than surface conditions. A super-Earth is not necessarily Earth-like. It may be a dense rocky planet with crushing gravity, a water-rich world, or a small planet carrying a thick atmosphere. Many Neptunes occupy a nearby range and often retain hydrogen-rich envelopes. Our solar system jumps from Earth to Neptune with nothing between. The galaxy does not. When astronomers plotted the sizes of many close-orbiting small planets, They found a deficit around roughly 1.5 to 2 Earth radii, often called the radius valley. Planets tend to fall on one side as smaller rocky worlds, or on the other as larger sub-Neptunes with gas envelopes. Young planets may begin with hydrogen and helium captured from the surrounding disk. Strong radiation from the star can heat and remove the atmosphere, leaving a bare core. The planet's own cooling interior can also drive mass loss. The exact contribution of photoevaporation and core-powered loss is still studied. The valley shows that a planet's present size records its history. Two worlds can begin similarly and diverge because of stellar radiation, mass, orbit, and time. Planet formation is not one act. It continues through migration, collision, escape, tides, and atmospheric chemistry. Some systems are arranged in resonant chains. Orbital periods form near simple ratios, so gravitational interactions repeat in an organized rhythm. The 7 planets of TRAPPIST-1 participate in a linked chain of near-resonant orbital relationships. The system's timing helped reveal planet masses because each world slightly advances or delays the transits of its neighbors. Other systems appear dynamically chaotic or widely spaced. Some giant planets move on highly eccentric orbits, passing close to the star and then far away. Some orbit backward relative to the star's rotation or travel over its poles. These misalignments suggest scattering, companion stars, warped disks, and tidal evolution. A planetary system can be rearranged long after formation. The solar system also carries signs of movement. Its giant planets likely migrated early. Small bodies were scattered. Earth formed through collisions. The moon probably arose from a giant impact. The difference is not that our system remained orderly while others became violent. The difference is degree, timing, and survival. Planetary systems are histories written as orbits. Once planets became common, habitability became the next temptation. A star has a region around it where the amount of received energy could allow liquid water on a planetary surface under suitable atmospheric conditions. This is the circumstellar habitable zone. The phrase is often shortened to Goldilocks zone, not too hot, not too cold. The simplicity is useful and dangerous. Distance alone does not create an ocean. Venus receives less than twice the sunlight Earth receives and is similar in size, yet its surface is hot enough to melt lead. A dense carbon dioxide atmosphere produces an immense greenhouse effect. Mars lies near the outer part of the Sun's traditional habitable region. Liquid water flowed across its surface in the distant past. Today, its atmosphere is thin, its surface cold and dry, and stable liquid water is rare. Earth lies between them. 3 rocky planets near one star demonstrate that orbit is only the beginning. A planet needs an atmosphere with the right pressure and composition. It needs a history that has not removed all surface water. Clouds can warm or cool. Continents and oceans redistribute heat. Rotation changes circulation. Volcanism releases gases. Weathering can remove carbon dioxide. A magnetic field may reduce some forms of atmospheric loss, though Venus shows that an atmosphere can remain thick without an Earth-like global magnetic field. The habitable zone is therefore a screening tool. It identifies where surface liquid water is physically plausible under modeled conditions. It does not identify inhabited planets. Even its boundaries depend on assumptions. Near the inner edge, warming increases evaporation. Water vapor is itself a greenhouse gas. More vapor produces more warming, which produces more vapor. A moist greenhouse can carry water high into the atmosphere, where ultraviolet light breaks molecules apart and hydrogen escapes to space. A full runaway greenhouse can vaporize oceans and make stable recovery difficult. Near the outer edge, carbon dioxide can strengthen warming until scattering sunlight and condensation limit the effect. Clouds of carbon dioxide or other gases may alter the boundary. Hydrogen released by volcanoes could extend warmth farther outward under some conditions. Planetary mass matters. A small planet loses atmosphere more easily. A massive rocky planet may hold dense gases and experience high pressure. The amount of water matters. An ocean-covered world may regulate climate differently from a world with continents. A dry planet can sometimes remain temperate closer to its star because little water vapor is available to amplify greenhouse warming. Habitability is not one ring drawn around a star. It is a relationship among star, orbit, atmosphere, surface, interior, and time. The star changes with age. Young sun-like stars are fainter than their mature forms. Later, luminosity rises gradually. A planet can enter or leave the habitable zone while remaining in the same orbit. Earth has stayed habitable despite a sun that was substantially fainter billions of years ago. Greenhouse gases, surface conditions, biology, and geological cycles helped compensate. This history leads to the idea of a continuously habitable zone, a region where suitable conditions might persist for enough time for life to originate and evolve. Time may matter as much as temperature. A planet that becomes temperate for 10 million years is different from one stable for billions. The atmosphere of Earth was not always breathable. Early Earth had almost no free oxygen. Microbial life existed for a long interval before oxygen accumulated substantially in the atmosphere. Photosynthetic organisms produced oxygen, but rocks, oceans, volcanic gases, and reduced minerals consumed it. The Great Oxidation Event around 2.4 billion years ago changed atmospheric chemistry, yet oxygen remained below modern levels for much of subsequent history. If a distant telescope had observed Earth during its first half, it might have missed the gas most commonly associated with complex life today. Earth itself warns against searching for one modern version of Earth. A living planet can be inhabited and spectroscopically unfamiliar. The size of a planet is easier to measure than its surface. Kepler 452b was widely described as an Earth cousin because it orbits in the habitable zone of a sun-like star and has a longer year. Its radius is larger than Earth's, and its mass and atmosphere remain poorly constrained. It could be rocky. It could carry a thick volatile envelope. A name in a catalog does not make a landscape. Other planets are more favorable for follow-up because their stars are nearby or small. When a small planet transits a small star, it blocks a larger fraction of the light. Its atmosphere also represents a larger signal relative to the star. This makes red dwarfs central to the search. Red dwarfs, also called M-dwarfs, are the most common stars in the Milky Way. They are cooler, smaller, and dimmer than the Sun. Their habitable zones lie close. A planet may complete an orbit in days or weeks while receiving an Earth-like amount of energy. The close orbit improves transit probability and allows many transits to be observed. It also creates challenges. Tidal forces can synchronize rotation. One side of the planet may face the star continuously while the other faces away. Early discussions pictured the day side as a scorched desert and the night side as a frozen trap where the atmosphere might collapse. Climate models found a more flexible outcome. If the planet has a substantial atmosphere or ocean, winds and currents can transport heat. Clouds may form over the illuminated region and reflect starlight. A ring near the terminator between day and night could remain temperate. Tidal locking is not automatically fatal to habitability. It produces a climate unlike Earth's. Red dwarf activity may be more serious. Young and active M-dwarfs produce strong flares, ultraviolet radiation, X-rays, and particle events. Because the habitable zone lies close, planets receive intense space weather. Radiation can break atmospheric molecules apart and drive escape. It can damage exposed biology. It can also create chemical reactions that imitate biosignatures or help prebiotic chemistry. The star evolves too. Red dwarfs spend a long, early phase brighter relative to their later settled output. A planet now in the habitable zone may once have received enough energy to lose an ocean. Whether an atmosphere survives depends on its original mass, magnetic environment, volcanic replenishment, water inventory, and stellar history. Some planets may be stripped bare. Others may retain thick atmospheres. The nearest potentially temperate exoplanet illustrates both hope and uncertainty. Proxima Centauri is the nearest star to the Sun, just over 4 light-years away. It is a small red dwarf and a member of the broader Alpha Centauri system. In 2016, astronomers announced Proxima Centauri b through radial velocity measurements. The planet has a minimum mass near Earth's range and orbits where the stellar energy could permit temperate conditions. It does not transit from our viewpoint. Its radius is unknown. Its atmosphere has not been detected. Its true mass depends on inclination. Proxima is an active flare star. The planet may have lost atmosphere and water. It may retain them through a combination of initial inventory and replenishment. It may be tidally locked. It may possess no stable surface water at all. Proxima b is often called potentially habitable. The accurate meaning is narrower. Its orbit and minimum mass do not exclude habitability. That is not the same as evidence for an inhabited or even temperate surface. A more elaborate natural laboratory lies about 40 light-years away. TRAPPIST-1 is an ultracool red dwarf only slightly larger than Jupiter in radius, though much more massive. 7 known planets cross its face. All are close to Earth in size. Their orbits fit inside a distance much smaller than Mercury's orbit around the Sun. The system was discovered in stages by a small telescope in Chile and follow-up observations, including NASA's Spitzer Space Telescope. Its name comes from the TRAPPIST telescope project and playfully reflects Belgian TRAPPIST tradition. The planets form a resonant chain. Their gravitational interactions shift transit times, allowing masses and densities to be estimated without the tiny radial velocity measurements that would otherwise be required. Several receive stellar energy broadly compatible with temperate climates under some atmospheric conditions. TRAPPIST-1e is often considered the strongest surface habitability candidate in the system. Planets F and G receive less energy, but could remain warm with appropriate atmospheres. Planet D lies near the inner side of the temperate region. The James Webb Space Telescope has begun testing these possibilities. Observations of the hot inner planets B and C indicate that they do not possess thick carbon dioxide atmospheres like Venus. They may have little atmosphere or much thinner and different gases. In 2025, Webb observations showed that TRAPPIST-1d does not have an Earth-like atmosphere. A thick carbon dioxide-rich, methane-rich, or broadly Earth-like atmosphere was disfavored by the data. This result did not answer the whole system. Initial Webb observations of TRAPPIST-1e have already made a surviving primordial hydrogen-helium atmosphere unlikely and disfavored clear carbon dioxide-dominated analogs of Venus or Mars. They have not established whether the planet is bare or carries a thinner secondary atmosphere. The atmospheres of E, F, and G remain much more difficult to characterize because the planets are cooler and their signals are smaller. The star itself complicates transmission spectra. Its surface contains regions of different temperatures. As a planet transits across one part, while unocculted spots and bright areas remain elsewhere, the stellar spectrum can imitate atmospheric absorption. The problem is called stellar contamination or the transit light source effect. A planet may be simple while its star makes the spectrum complex. Years of repeated observations may be needed. TRAPPIST-1 is therefore not a discovered inhabited system. It is a test of whether current astronomy can distinguish atmosphere from star on small rocky worlds. Even a negative result matters. If the planets are bare, scientists learn how red dwarf radiation removes atmospheres. If some retain gases, they learn which worlds survive. If compositions differ across neighboring planets, the system becomes a controlled experiment in mass, irradiation, and formation. The absence of life is not the only scientific answer. Planetary survival itself is part of the search. Other nearby systems offer different possibilities. LHS 1140b is a larger rocky or water-rich planet orbiting a quiet red dwarf. Its density and atmospheric observations have led to proposals that it may contain a large water fraction and possibly a liquid region beneath a thick atmosphere, though current data do not prove an ocean. TOI 700 hosts small planets, including one in the star's habitable zone. The star is relatively quiet for an M dwarf, but atmospheric characterization remains difficult. The list changes as masses and radii improve. A promising planet can move out of the rocky category when its mass is measured. A planet thought temperate can prove too hot when clouds or atmosphere are observed. A system dismissed as active can reveal atmospheric survival. Habitability is not a label awarded once. It is a hypothesis repeatedly tested. The most important unknown may be atmosphere. Without it, a habitable zone planet can be an airless rock. With too much, it can become a high-pressure furnace. With the right composition and circulation, it may support liquid water. To learn which, astronomers must do more than detect a transit. They must read the light that passes through the thin shell around a distant world. Atmospheric spectroscopy turns a planet into a filter. During transit, a small fraction of starlight passes through the planet's atmosphere before reaching the telescope. Atoms and molecules absorb particular wavelengths according to quantum transitions. Water, methane, carbon dioxide, carbon monoxide, ozone, sodium, potassium, and other species leave patterns. The pattern is not one clean missing line. Absorption bands overlap. Clouds hide deeper layers. Hazes scatter short wavelengths. Temperature changes the strength of features. Pressure broadens them. The star contributes its own spectrum. The planet's atmosphere may extend only a few scale heights above the opaque body. For a small rocky planet, the additional area is tiny. One transit does not provide a photograph of an atmosphere. It provides a slight difference between two measurements of starlight. Astronomers combine repeated transits, calibrate detector behavior, model the star, and compare many possible atmospheric compositions. Different data reduction pipelines can produce slightly different spectra. Different retrieval codes can prefer different molecules. A retrieval is a statistical inference. The code generates spectra from possible temperatures, clouds, and chemical abundances, then asks which combinations fit the data. It does not simply look at a feature and read the name of a molecule. If two molecules absorb in similar regions, the solution can be degenerate. If the model excludes one plausible molecule, another may appear more significant than it should. The search for life depends on understanding this uncertainty. A biosignature is not merely a molecule associated with life on Earth. It is an observation best explained by life after plausible non-biological sources and observational errors have been tested. Oxygen is the classic example. On Earth, most atmospheric oxygen is produced by photosynthesis. Large amounts of oxygen can also support ozone, which has strong spectral features. Yet oxygen can accumulate without biology under some planetary conditions. Ultraviolet light can break water vapor apart. Hydrogen escapes more easily than oxygen, leaving oxygen behind. Carbon dioxide can be photochemically split. A planet that lost an ocean may retain an oxygen-rich atmosphere that records catastrophe rather than life. Context can reveal the difference. Very large oxygen abundance, carbon monoxide, absence of water, or the star's ultraviolet spectrum may support an abiotic explanation. Methane also has biological and geological sources. On Earth, microorganisms produce much methane. But water-rock reactions such as serpentinization can generate hydrogen that participates in methane formation. Volcanoes and impacts contribute. The rate and environment matter. Oxygen and methane together are interesting because they react and require replenishment. But even atmospheric disequilibrium is not a universal proof. Scientists must calculate sources, sinks, ocean chemistry, surface minerals, stellar radiation, and atmospheric escape. Nitrous oxide is produced biologically on Earth and has fewer obvious abiotic sources at high abundance, but it may be difficult to detect. Methyl chloride, dimethyl sulfide, and other gases have been proposed. Each has photochemical pathways and uncertainties. A biosignature could also be a pattern rather than one gas. Seasonal changes might show biological cycling, but seasons can be produced by condensation, circulation, or orbital variation. Surface pigments might create a vegetation like red edge, where reflectance rises sharply at certain wavelengths. Minerals and non-Earth photosynthetic pigments could produce different edges. Life may not advertise itself in the forms Earth uses now. The history of Earth provides several possible exoplanets in one body. A young Earth with a faint sun, volcanic gases, and no oxygen would look different from the Proterozoic Earth with microbial life and modest oxygen. The Carboniferous atmosphere differed from the modern atmosphere. Ice-covered intervals changed reflectivity. Continents moved. Biological productivity varied. If an alien telescope observed Earth at random across 4 billion years, the chance of seeing modern oxygen, forests, and city lights together would be small. A biosignature search must therefore recognize inhabited planets that do not resemble the present Earth. It must also avoid announcing life on planets that resemble no known habitat. K218b became the clearest modern example of both excitement and restraint. The planet orbits a red dwarf about 120 light-years away. Its radius is roughly 2.5 times Earth's, and its mass is several times larger. It is not an Earth twin. Its size places it in the sub-Neptune category, a kind of planet absent from the solar system. Some models allow a deep global ocean beneath the hydrogen-rich atmosphere. These proposed planets have been called Hycean worlds, combining hydrogen and ocean. Other models produce a gas-rich mini-Neptune with no accessible liquid surface, a high-pressure water layer, a supercritical interior, or a magma-related environment. Mass and radius do not decide among them. In 2023, a team analyzing James Webb observations reported methane and carbon dioxide in the atmosphere and a tentative hint of dimethyl sulfide. On Earth, dimethyl sulfide is strongly associated with marine biological activity, especially microorganisms and phytoplankton-related ecosystems. The possibility drew global attention. The signal was weak. In 2025, the same team reported mid-infrared features that could be fit by dimethyl sulfide, dimethyl disulfide, or a combination. The statistical preference was described as suggestive rather than a discovery. Headlines moved faster than the evidence. Independent groups reprocessed the observations with other pipelines and retrieval models. They found that methane was the most robust molecular result. Carbon dioxide was less secure than initially claimed in some analyses. Evidence for dimethyl sulfide or dimethyl disulfide did not remain statistically significant when broader wavelength coverage, alternative reductions, additional molecules, and instrumental systematics were considered. One analysis found that molecules with similar absorption could fit as well. Another found that the mid-infrared spectrum was sensitive to wavelength binning and red noise. By 2026, detailed atmospheric models could explain the data as a hazy, metal-rich sub-Neptune shaped by disequilibrium chemistry without requiring a biosignature. This does not prove that K218b is lifeless. It means the available observations do not provide reliable evidence for life. The distinction is central. A molecule may be biologically produced on Earth. Its possible spectral feature may be present at low significance. The planet may not have a habitable surface. The instrument may contain systematic noise. Each statement must be tested separately before they are combined into a claim about life. K218b is not an embarrassment for astrobiology. It is astrobiology working in public. A dramatic interpretation was proposed. Other scientists tested the data. The result became more cautious. The process showed what future biosignature claims will require: independent reductions, repeated observations, more than one instrument, laboratory measurements of molecular absorption, models of stellar contamination, plausible atmospheric and interior chemistry, a framework for ranking evidence rather than one threshold announced in a press release. The first true exoplanet biosignature may begin in exactly this uncertain way. One team will notice a feature. Another will challenge it. More observations will strengthen or remove it. Alternative chemistry will be proposed. The host star will be measured. The planet's mass and climate will be refined. Certainty, if it comes, will be accumulated. James Webb was not designed as a dedicated Earth twin finder. Its large mirror and infrared instruments make it extraordinarily capable, but the atmosphere of a temperate Earth-sized planet around a sun-like star is beyond its routine reach. The planet transits only once per year. The signal is tiny. The star is large. Clouds can erase features. Many transits would require years and may still be insufficient. Webb is more effective for giant planets, sub-Neptunes, and small planets around small stars. It has detected carbon dioxide in giant exoplanet atmospheres, measured temperature maps, identified clouds and photochemistry, and tested whether rocky planets around red dwarfs retain atmospheres. These results build the methods needed for later missions. There are other ways to study atmosphere. When a planet passes behind its star, the combined light decreases by the amount contributed by the planet. This secondary eclipse measures thermal emission or reflected light. Observations across an orbit create a phase curve, showing how brightness changes as different portions of the planet face Earth. A hot Jupiter can reveal winds carrying heat from day to night. The hottest point may be shifted east or west of the substellar point. Clouds can form on one side and evaporate on another. High-resolution spectroscopy can separate a planet's rapidly moving spectral lines from the slower stellar and terrestrial signals. Molecules can be detected through repeated line patterns even when the planet is not spatially resolved. Future large ground telescopes may combine high resolution with powerful adaptive optics to study nearby rocky planets around red dwarfs. Direct imaging offers the clearest path toward true analogs around sun-like stars. A coronagraph must suppress starlight by factors of billions while controlling tiny optical distortions. A starshade must maintain formation across tens of thousands of kilometers and align its shadow precisely. The planned Habitable Worlds Observatory is being designed around this challenge. NASA's current objective is to directly image and characterize on the order of a few dozen potentially habitable worlds, with a working target of about 25. The mission remains in development and technology maturation rather than at a fixed launch date. Its telescope would use ultraviolet, visible, and infrared light to search atmospheres for water, oxygen, methane, and context. Even HWO will not deliver a simple life detector. A spectrum will need planetary mass, orbit, stellar history, clouds, surface conditions, and chemical modeling. The goal is not to find one magic line. It is to build a planetary case. Before applying that case to distant worlds, scientists study the only inhabited planet and the nearest uninhabited ones. Earth, Mars, Venus, Titan, Europa, and Enceladus are not distractions from exoplanets. They are the laboratory in which the meaning of habitability is learned. Mars preserves the memory of a more habitable world. Dry valleys, deltas, lake beds, altered minerals, and sedimentary rocks show that liquid water once moved across its surface. The early atmosphere was thicker. Rivers entered craters and built fans. Lakes persisted long enough to sort and deposit sediment. Whether Mars ever became inhabited remains unknown. The planet lost much of its atmosphere as its interior cooled, magnetic environment changed, and solar radiation stripped gases into space. Water froze underground, became locked in minerals, or escaped. Robotic missions searched for environments that could have supported ancient microbes and for chemical or textural signs they may have left. Organic molecules have been detected in Martian rocks and atmosphere. Organic does not mean biological. Carbon chemistry forms in meteorites, interstellar space, hydrothermal systems, and planetary atmospheres without life. A biosignature on Mars would need context, structures, isotope patterns, mineral associations, repeated evidence, and contamination control. The Viking landers performed the first direct life detection experiments on another planet in 1976. One experiment produced a response when nutrient solution was added to Martian soil. Other instruments did not find the expected organic material, and the result was interpreted mainly as reactive soil chemistry rather than metabolism. Decades later, perchlorate salts and complex surface chemistry showed that the interpretation was more difficult than scientists had known. Viking remains a lesson in designing experiments before the environment is fully understood. A test for life is also a test for unexpected chemistry. Venus offers a different warning. It is almost Earth-size and may once have had surface water. Today, its lower atmosphere is dense carbon dioxide beneath clouds of sulfuric acid. The surface temperature is around 465 degrees Celsius. The cloud layers dozens of kilometers above the surface have temperatures and pressures closer to familiar terrestrial conditions. This led Harold Morowitz and Carl Sagan to discuss possible cloud life in the 1960s, and the idea never vanished entirely. In 2020, astronomers reported phosphine in Venus's atmosphere. On Earth, phosphine can be associated with biology in oxygen-poor environments, though it also forms through industrial and some geological processes. The claimed spectral line became controversial immediately. Other analyses found weaker signals, no signal, or contamination from sulfur dioxide. Calibration and processing choices mattered. The chemistry of Venus remained incomplete. The phosphine case has not produced confirmed evidence of life. The clouds also present a severe water problem. Their droplets are concentrated sulfuric acid with extremely low water activity, below known limits for terrestrial organisms in many estimates. Unknown biology cannot be ruled out by definition, but habitability must be more than temperature alone. Future Venus probes can sample cloud particles directly and measure chemistry with instruments designed for the question. A local measurement can escape ambiguities that burden distant spectra. Farther from the Sun, worlds with no surface sunlight may contain oceans. Europa, one of Jupiter's large moons, has an ice shell covering a global salty ocean. Tidal flexing by Jupiter and neighboring moons supplies internal heat. The surface displays ridges, fractures, disrupted regions, and young terrain. Magnetic measurements by the Galileo spacecraft supported a conductive layer consistent with salt water beneath the ice. The ocean may contain more water than Earth's oceans. Water alone does not establish habitability. Life also needs usable energy and chemical ingredients. If Europa's ocean interacts with a rocky seafloor, water-rock reactions could create chemical gradients. Oxidants formed at the irradiated surface might move downward through cracks, overturn, or geological recycling. The thickness and dynamics of the ice shell remain uncertain. NASA's Europa Clipper launched in October 2024. It used Mars for a gravity assist in March 2025 and is scheduled to return past Earth in December 2026 before reaching Jupiter in 2030. The spacecraft will orbit Jupiter and make nearly 50 close flybys of Europa. Its radar will probe ice structure. Spectrometers will map surface chemistry. Magnetometer and gravity measurements will constrain the ocean and interior. Cameras will examine geology. Instruments may sample particles if material rises above the surface. Europa Clipper is not a direct life detection mission. It asks whether Europa contains places and chemical conditions that could support life. Habitability comes before inhabitants. Enceladus allows the ocean to come to the spacecraft. The small moon of Saturn ejects jets of water vapor and ice grains from fractures near its south pole. Cassini flew through the plumes. The particles contain salts, organic compounds, silica nanoparticles, molecular hydrogen, and phosphorus. Silica particles suggest hot water interacting with rock. Molecular hydrogen can be produced through hydrothermal reactions and could provide chemical energy for microbes like some found near Earth's seafloor. Phosphate detected in ice grains suggests that phosphorus may be abundant in the ocean. Enceladus therefore contains liquid water, bioessential elements, organic chemistry, and energy gradients. It is habitable in a chemical sense. No observation has shown that it is inhabited. The distinction can feel frustrating because all the ingredients seem present. Yet a kitchen containing ingredients does not prove that a meal has assembled itself. The origin of life is a transition whose probability remains unknown. Titan, another moon of Saturn, expands the search beyond water at the surface. Its thick nitrogen atmosphere produces organic haze. Methane clouds, rain, rivers, and lakes create a weather cycle at temperatures far below the freezing point of water. Liquid methane and ethane occupy the surface, while a water ocean may exist deep below. Titan is rich in carbon chemistry. Life based on familiar liquid water biochemistry would struggle at the surface because reactions proceed slowly and water is frozen hard as rock. More exotic solvent systems have been proposed, but no example of life using liquid methane is known. Titan is valuable because it shows complex prebiotic chemistry in a planetary environment. NASA's Dragonfly mission is designed to send a rotorcraft to Titan to examine surface chemistry and habitability at multiple locations. The solar system provides several kinds of almost. Mars may have been habitable in the past. Venus may once have been temperate and may contain chemically intriguing clouds. Europa and Enceladus hide oceans beneath ice. Titan has abundant organic chemistry under alien conditions. Earth alone has confirmed life. This single example limits every probability estimate. Life arose early in Earth's history, perhaps within several 100 million years after stable conditions became available. That speed is sometimes used to argue that life begins readily. The reasoning contains a selection effect. Observers can only arise on a planet where life began early enough to permit later evolution. If abiogenesis were extremely rare, we would still necessarily find ourselves on one of the rare successful worlds. One inhabited planet cannot reveal the general frequency. To understand the transition, researchers study prebiotic chemistry. Early Earth contained water, gases, minerals, volcanic systems, impacts, ultraviolet light, and chemical gradients. Organic molecules also arrived in meteorites. Amino acids, nucleobases, sugars, lipids, and related compounds can form through several non-biological pathways. The famous Miller-Urey experiment in 1953 sent electrical sparks through a model atmosphere and produced amino acids. The exact gas mixture did not represent all of early Earth, but the results showed that biological building blocks can emerge from simple chemistry. Later experiments used volcanic gases, ultraviolet radiation, ice, mineral surfaces, hydrothermal conditions, and wet-dry cycles. The difficult step is not making one organic molecule. It is creating a system that stores information, uses energy, maintains a boundary, reproduces with variation, and evolves. RNA is a leading part of many origin scenarios because it can carry information and catalyze reactions. Modern cells use RNA in protein synthesis, and some RNA molecules act as enzymes. An RNA world may have preceded DNA and proteins, but how long RNA strands formed, copied reliably, and became enclosed remains unresolved. Metabolism first models emphasized networks of reactions on mineral surfaces or at hydrothermal vents. Lipid compartments can form spontaneously in water and create primitive boundaries. Wet-dry cycles can concentrate molecules and promote bonds. Several environments may have contributed rather than one exact cradle. Life on Earth may have originated once, or several origins may have occurred with only one lineage surviving. All known organisms share deep features: genetic coding, ribosomes, cellular membranes, and common chemistry. This unity suggests a common ancestor, but does not reveal whether chemistry crossed into life only one time. The last universal common ancestor was already biologically sophisticated. It was not the first living system. Its earlier history has largely been erased by later evolution. Extremophiles show what life can do after it exists. Microorganisms live in acidic mine drainage, salt-saturated water, deep rock, Antarctic ice, hot hydrothermal systems, and high radiation environments. Some survive pressure, dehydration, or chemical conditions lethal to humans. These organisms do not prove that life can originate under every extreme. Adaptation and origin are different. A lineage can begin under mild conditions and later evolve tolerance. Still, extremophiles widen the range of habitats worth investigating. They also change how scientists interpret atmospheric gases. A planet's biosphere may be microbial and hidden underground. It may produce little global signal. Life could be common while detectable biospheres remain rare. Earth's atmosphere became strongly modified because photosynthesis spread across the planet. A sparse subsurface biosphere on Mars or Europa might never alter an atmosphere enough to be seen from another star. The search for life has an observational bias toward abundance. It is easiest to detect life that changes an entire planet. The first extraterrestrial organism, if found locally, may be one cell or one chemical pattern. The first exoplanet biosignature, if found remotely, may imply a biosphere operating at global scale. These would answer different questions. One would show that life began twice. The other would show that life can transform a world. Both would change the meaning of the night sky. The phrase life as we know it contains both humility and limitation. Every confirmed organism uses carbon-based chemistry and liquid water. Cells store information in nucleic acids, build proteins from amino acids, and maintain boundaries through membranes. Carbon is unusually versatile. It forms stable chains, rings, branches, and bonds with hydrogen, oxygen, nitrogen, sulfur, phosphorus, and metals. Water dissolves many substances, participates in reactions, remains liquid across a useful temperature range under appropriate pressure, and supports the folding and motion of biological molecules. These properties make carbon and water-strong targets beyond Earth. They do not prove that no other chemistry can support evolution. Silicon is often proposed because it can form 4 bonds like carbon. Yet silicon-silicon chains are generally less versatile under familiar planetary conditions, and silicon combines readily with oxygen to form solid minerals. Liquid methane can act as a solvent on Titan, but reactions proceed differently at such low temperatures. Ammonia, mixtures of water and ammonia, supercritical carbon dioxide, and other fluids have been discussed. No alternative system is known to be alive. Astrobiology therefore begins with terrestrial chemistry because it is the only demonstrated example, while keeping broader physical principles in view. Life must maintain organization away from equilibrium. It must use energy. It must preserve information with enough stability for inheritance and enough variation for evolution. It must separate itself partly from the environment while exchanging matter and energy. These requirements may be more universal than DNA or oxygen. A search based only on familiar molecules could miss unfamiliar life. A search broad enough to include every complex chemical pattern could mistake non-biological chemistry for organisms. Researchers have proposed agnostic biosignatures that do not assume one exact biochemistry. One approach examines molecular complexity. Living systems can produce distributions of molecules that are difficult to assemble through random or simple geochemical pathways. Repeated complex structures, selected from many possibilities, may indicate a process maintaining specific products. Another approach searches for chemical disequilibrium, combinations that should react away unless a continuous process replenishes them. Another examines isotope fractionation. Biological reactions often favor lighter isotopes slightly, leaving measurable patterns. Geological processes can also fractionate isotopes, so context remains essential. Chirality provides another idea. Many molecules occur in mirror image forms. Earth life uses strong preferences. Proteins mainly contain one-handedness of amino acids, while sugars and nucleic acids use another. Non-biological chemistry often produces more balanced mixtures, though physical processes can create asymmetry. A strong and organized chiral excess in a sample could support biology, especially with other evidence. These methods are easier in a return sample or a plume than across interstellar distance. A telescope receives broad molecular bands, not individual cells. Future instruments may search for polarization patterns associated with chiral molecules or surfaces, but such measurements would be extremely demanding. Alien life may also alter its planet in ways no Earth organism does. A photosynthetic system around a red dwarf could use wavelengths different from terrestrial plants because the stellar spectrum is redder and flares alter ultraviolet conditions. Pigments might appear dark, infrared reflecting, or almost black to human eyes. Oxygenic photosynthesis may not evolve. Another gas may become the dominant waste product. A biosphere could live beneath clouds and leave only subtle atmospheric effects. Even the concept of a surface may be local. Life could float in a thick atmosphere, occupy pores in ice, live within rock, or circulate through an ocean beneath hundreds of kilometers of high-pressure ice. Some environments may support chemistry without a stable boundary between sea and air. A planet called uninhabitable from surface temperature could contain habitable layers above or below. This flexibility does not mean every planet deserves equal optimism. Physical constraints remain. Complex chemistry requires suitable temperatures or alternative mechanisms. Energy gradients must persist. Solvents must remain available. Radiation can both drive chemistry and destroy molecules. Nutrients must circulate rather than becoming permanently inaccessible. A giant planet atmosphere may contain a temperate altitude, but no stable way for organisms to avoid sinking into hotter depths. An ocean beneath high-pressure ice may be separated from rock and nutrient sources. A cloud habitat may be too dry. Habitability is not the ability to imagine one comfortable point. It is the ability of an environment to support cycles across time. The most cautious search, therefore, uses several levels. First, identify environments where chemistry can operate. Then search for molecules or structures that exceed expected abiotic complexity. Then test whether energy, material cycling, and stability can maintain the inferred biology. Finally, repeat the observation with another method. This approach cannot guarantee recognition of truly alien life. It reduces the chance that unfamiliarity becomes either automatic rejection or automatic wonder. The first alien biosphere, if discovered, may be strangely familiar in some ways. It may use carbon because carbon is effective. It may use membranes because compartments solve a universal problem. It may evolve because selection follows from imperfect replication. And it may remain profoundly different in genetic code, metabolism, cellular structure, ecology, and sensory world. One discovery would not reveal the full range. Earth contains bacteria, forests, fungi, whales, and humans within one shared ancestry. A second origin could produce diversity beyond any one sample. The phrase alien life sounds like a category. It may contain more variation than all life on Earth. The search becomes statistical when direct evidence ends. How many stars form? How many have planets? How many planets offer suitable environments? How often does life begin? How often does it become detectable? How long does the detectable state last? In 1961, radio astronomer Frank Drake organized these questions for a meeting at Green Bank, West Virginia. The meeting gathered a small group to discuss communication with extraterrestrial intelligence. Drake needed an agenda. He wrote an equation. The Drake equation multiplies several terms to estimate the number of technological civilizations in the Milky Way whose signals might be detectable. It begins with astronomy, the rate at which suitable stars form, the fraction with planets, and the number of potentially habitable worlds per system. It then enters biology and society, the fraction where life begins, the fraction where intelligence evolves, the fraction that develops detectable technology, and the duration of that detectable phase. The equation is sometimes treated as a calculator that can prove the galaxy crowded or empty. It cannot. The early astronomical terms have improved dramatically. Planets are common. Small worlds occur throughout the known exoplanet population. Potentially temperate orbits exist. The later terms remain almost unconstrained. We know one planet where life began, one lineage that produced radio technology, and only about a century during which Earth has been strongly detectable through some forms of technological emission. A product containing several unknown probabilities can produce nearly any answer. The equation's value is organizational. It shows which discoveries change the estimate. Exoplanet surveys constrain planetary occurrence. Mars or Enceladus could constrain the frequency of life if an independent biosphere were found. Atmospheric surveys could constrain detectable biology. SETI constrains certain forms of technology over certain frequencies, distances, and times. The final term, longevity, may dominate. A civilization could produce detectable radio leakage for a century and then switch to quiet communication. It could remain technologically active for 1,000,000 years. It could destroy itself. It could choose not to transmit. Its planet's atmosphere might carry industrial chemistry long after radio fades. Detectability is a behavior and an engineering state, not simply intelligence. The Drake equation also hides time. Two civilizations can arise in the same galaxy and never overlap. One may disappear 1,000,000 years before the other develops technology. Light from their planet can continue traveling, but deliberate conversation requires temporal coincidence across distance. The Milky Way is about 100,000 light-years across. A message to a civilization 1,000 light-years away takes 1,000 years to arrive. A reply takes another 1,000. Interstellar communication is not a telephone call. It is correspondence across history. These delays contribute to the question associated with Enrico Fermi. During a lunch conversation in 1950, Fermi and colleagues discussed flying saucers, travel, and the possibility of extraterrestrial civilizations. Fermi asked a version of "Where is everybody?" The exact wording and context come from later memories. The modern Fermi paradox is broader. If technological civilizations are common and capable of expanding through the galaxy, why is there no obvious evidence? The term paradox may be too strong. The premise has not been established. We do not know that technological civilizations are common. We do not know that they expand. We do not know which evidence would remain visible. We have searched only a small part of the relevant space. Still, the silence invites hypotheses. Perhaps the origin of life is extremely rare. Chemistry may produce organic molecules easily, but almost never produce self-sustaining evolution. If so, Earth passed an early improbable step. Perhaps microbial life is common and complex cells are rare. For most of Earth's history, life was microbial. The transition to eukaryotic cells involved internal structures and, according to the leading account, an ancient symbiosis that produced mitochondria. Complex multicellularity evolved more than once, but not immediately. Perhaps intelligence capable of technology is rare. Evolution has no predetermined direction toward radio astronomy. Dinosaurs occupied terrestrial ecosystems for more than 100 million years without building transmitters. Whales, octopuses, corvids, elephants, and primates evolved different forms of cognition. Human technological culture depended on anatomy, social learning, language, fire, environmental history, and cumulative transmission. A small change could have led elsewhere. Perhaps civilizations are common but short-lived. Technology can create environmental damage, weapons, engineered disease, or systems too complex to control. This idea appears in the Great Filter hypothesis. One or more steps between lifeless matter and long-lived expansion may be extraordinarily difficult. If the filter lies behind us, perhaps life or intelligence is rare. If it lies ahead, technological civilizations may repeatedly fail to survive. The Great Filter is not an observed law. It is a way of thinking about conditional probabilities. Finding simple life on Mars would change its emotional interpretation for some people. If life began independently nearby, abiogenesis might be easier, moving the unknown filter toward later steps. Finding no life in many suitable environments could move rarity earlier. These inferences would still depend on sample size and independence. Perhaps advanced civilizations become difficult to detect. Earth's radio leakage is not steadily increasing in every direction. Communication has shifted toward cables, fiber, satellites, spread spectrum signals, and lower power systems. Powerful radars remain detectable farther away, but beams do not illuminate every star continuously. An alien society could use communication methods we have not considered or direct narrow beams elsewhere. A civilization might build efficient technology whose waste signatures are subtle. It might remain within one planetary system rather than colonize the galaxy. Expansion is not inevitable. Biological motives shaped by scarcity and reproduction on Earth may not apply universally. Interstellar travel is difficult. Machines can cross slowly, but settlement decisions involve values, not physics alone. Perhaps evidence exists but looks natural. A technological structure may resemble dust. Atmospheric pollution may have geological sources. A narrow radio signal may be terrestrial interference. Artificial illumination may be too faint. The search must avoid defining intelligence as whatever remains unexplained. Unexplained is a temporary category, not a technosignature. Some suggested resolutions are more speculative. Civilizations might avoid young worlds, creating a so-called zoo. They might communicate through channels inaccessible to us. They might enter virtual environments. They might hide for security. We may live before the main era of intelligence or after it. These ideas can be imagined without being tested easily. Science advances where hypotheses produce observations. The rare Earth hypothesis approaches the problem from planetary conditions. Complex life on Earth may depend on a long sequence. A stable star suitable orbit, retained water, climate regulation, plate tectonics, or another recycling mechanism, a protective atmosphere, nutrient supply, a large moon, giant planets, and a history of extinctions that neither sterilized the world nor ended evolution. Some items on this list are uncertain or overstated. Jupiter can deflect some comets and redirect others inward. A large moon stabilizes Earth's tilt, but planets may remain stable through other architectures. Plate tectonics supports Earth's carbon cycle, yet stagnant lid planets could regulate climate differently. Complex life may tolerate conditions unlike ours. The useful insight is not that Earth passed one established checklist. It is that habitability over billions of years depends on history. A planet can begin in the right orbit and lose water. A stable climate can be interrupted by impacts, volcanism, or stellar change. Nutrients can limit productivity. Oxygen can remain low. Microbial life and technological life may have very different requirements. The galactic habitable zone extends the idea outward. Regions near the galactic center have high stellar density, radiation, and explosive events. Farther out, heavy elements needed for rocky planets may be less abundant, especially in earlier cosmic history. The solar system lies at an intermediate galactic radius. Yet metallicity has varied with time. Rocky planets form across a broad range, and the danger from supernovae depends on local history rather than one permanent ring. The galaxy is not divided into a simple safe annulus and sterile remainder. Life may thrive in locations we would rank poorly from one variable. The probability question remains open because every scale contains context. A habitable planet may not produce life. A living planet may remain microbial. A complex biosphere may not produce intelligence. An intelligent species may not produce detectable technology. A technological civilization may not overlap with us. The multiplication can reduce large numbers rapidly. But the Milky Way contains hundreds of billions of stars and has existed for more than 13 billion years. Even rare events may occur more than once. The argument can be made in both directions because the unknown probabilities are large enough to absorb intuition. This is why observation matters. One independent microbe would change the first biological term. One atmospheric biosignature would show that planetary scale life is not unique. One technosignature would answer the central question immediately. Until then, the galaxy's silence is not a conclusion. It is the current result of incomplete listening. Scientific listening began before exoplanets were known. In 1959, physicists Giuseppe Cacconi and Philip Morrison published a short paper asking whether interstellar communication through radio waves might be possible. Radio travels through space at the speed of light. Certain frequencies pass through Earth's atmosphere and the interstellar medium with relatively little absorption. A sufficiently powerful narrowband transmitter could stand out from natural radio emission. The paper suggested looking near the frequency emitted by neutral hydrogen, about 1,420 MHz. Hydrogen is the most abundant element in the universe. Any civilization practicing radio astronomy would know the line. The reasoning did not imply that aliens must choose it. It offered a shared physical landmark. Frank Drake began Project Ozma in 1960 at the Green Bank Observatory. He pointed a radio telescope toward Tau Ceti and Epsilon Eridani, two nearby sun-like stars, and listened near the hydrogen line. The equipment searched for a narrow signal drifting in frequency as Earth and a distant planet moved. One early signal appeared. It vanished when the telescope moved off the star and returned when it moved back. For a moment, the pattern looked extraordinary. Investigation traced it to an aircraft. Project Ozma detected no extraterrestrial transmission. It established the method. Radio SETI became a search through several dimensions. The telescope chooses a direction on the sky, a frequency, a bandwidth, a time, a polarization, and a sensitivity. A signal may be continuous or pulsed, broad or narrow, repeating or transient. No survey can search all combinations. The relevant search space has been compared with an ocean. Humanity has sampled portions of it, sometimes deeply, often briefly. A non-detection constrains what could have been present in that particular observation. It does not show that no technology exists anywhere. Natural radio sources are often broadband. Thermal motion, magnetic fields, plasma, and astrophysical shocks spread power across frequencies. A signal narrower than known natural processes can be technologically suggestive. Yet human technology also produces narrow signals. Satellites, mobile networks, aircraft, radar, spacecraft, and local electronics fill radio observatories with interference. A candidate must be shown to come from the sky, from one direction, and preferably to repeat. Observatories compare beams and locations. A real distance source should follow the motion expected as Earth rotates. Terrestrial interference often appears in many directions or fails the pattern. The most famous candidate never repeated. On August 15, 1977, the Big Ear radio telescope at Ohio State University recorded a strong narrowband signal during a survey. The telescope used Earth's rotation to sweep the sky through its fixed beams. A source would rise and fall in intensity over 72 seconds, matching the time a point crossed the observing pattern. The printout encoded strength as characters. Astronomer Jerry Emmon later circled the sequence 6 EQUJ5 and wrote "Wow" beside it. The signal lay near the hydrogen line and followed the expected rise and fall. It was not heard again. Repeated searches of the region found nothing. Proposals have included terrestrial interference, a reflected signal, hydrogen around a comet, or an unusual astrophysical event. None has become a universally accepted explanation. The "wow" signal remains unexplained. Unexplained does not mean extraterrestrial. A confirmed technosignature would require repetition or independent evidence strong enough to eliminate ordinary sources. The signal's scientific value lies partly in its incompleteness. One observation can be fascinating and insufficient at the same time. Later SETI projects expanded the search. The SETI Institute's Project Phoenix examined nearby stars. Distributed computing projects such as SETI at Home allowed volunteers' computers to analyze radio data. Optical SETI searched for brief laser pulses. Surveys used the Allen Telescope Array, Green Bank Telescope, Parkes Observatory, Meerkat, and other instruments. Breakthrough Listen began in 2015 with the goal of conducting one of the broadest searches yet. It observes nearby stars, the galactic plane, and selected galaxies across radio and optical wavelengths. The program releases data so that independent researchers can develop methods and inspect candidates. Machine learning helps classify interference, though algorithms can also learn the biases in their training data. No confirmed technosignature has emerged. Several candidates have illustrated the process. In 2019, observations toward Proxima Centauri contained a narrowband signal later labeled BLC1. It appeared in some on-source observations and initially survived several checks. Because Proxima has a known planet and is the nearest star, the candidate attracted intense interest within the team before becoming public. Detailed analysis found related signals at other frequencies and behavior consistent with human made interference generated by interacting electronics. BLC1 was not a transmission from Proxima. The failure was useful. Researchers documented how a signal can mimic the expected properties and improved screening methods. SETI needs false alarms. A search that never produces candidates may not be sensitive enough. A rigorous search produces candidates and then removes them. The challenge is to keep public excitement from outrunning the removal stage. Deliberate beacons are only one possible target. Technological activity can create accidental signs. Earth emits radar. Its atmosphere contains industrial gases. The night side glows with artificial light. Large satellites and debris cross orbit. Solar panels and structures reflect light. Waste heat leaves every energy-using system. These potential technosignatures differ in detectability. Ordinary radio leakage from television and mobile communication becomes weak across interstellar distance. Powerful planetary radars can be detectable much farther if their narrow beams point toward an observer. A laser pulse can briefly outshine a star within an extremely narrow wavelength, but must be directed accurately. Industrial pollutants might accumulate in an atmosphere, yet the planet would need to transit or be directly imaged at sufficient resolution. City lights are vastly fainter than daylight reflected from a planet. A civilization using much more energy than humanity could be easier to see. In 1960, physicist Freeman Dyson suggested that a technologically advanced society might capture a large fraction of its star's energy. The popular image became a solid shell enclosing the star. A solid rigid sphere would face severe engineering and dynamical problems. Dyson's more general argument concerned a swarm of orbiting collectors. The structures would absorb starlight and re-radiate energy as infrared waste heat. A star unusually faint in visible light and bright in infrared could be a candidate. Astronomical surveys have searched for such spectral energy distributions. Dust also absorbs visible or ultraviolet light and emits infrared. Young stars, dying stars, debris disks, and dusty galaxies create natural excesses. No convincing Dyson swarm has been confirmed. The search, nevertheless, turns thermodynamics into observation. Technology cannot use energy without releasing waste heat at some temperature. The exact wavelength depends on engineering choices, but the principle is broad. Strange dimming events provide another route. Kepler observed the star K IC 8462852, later called Boyajian star or Tabby's star. Its brightness dropped irregularly, sometimes by more than 20%. Planets produce periodic, similarly shaped transits. These dips were deep and uneven. Astronomer Tabitha Boyajian and citizen scientists who helped identify the behavior considered several natural explanations. Public discussion expanded to alien megastructures. Follow-up observations showed that blue light was blocked more strongly than red light. An opaque structure would dim wavelengths more equally. Small dust particles naturally produce color-dependent extinction. Dust became the favored explanation, though the origin and arrangement of the dust remained unusual. The episode demonstrated the correct order. Notice an anomaly. Consider technology among possibilities if justified. Observe at more wavelengths. Prefer the explanation that fits all evidence with known physics. A technosignature should not be the explanation of last resort simply because natural models are incomplete. It should make positive predictions. Atmospheric technosignatures follow the same rule. Chlorofluorocarbons and related compounds can be produced industrially and remain in atmospheres. Nitrogen dioxide can arise from combustion and natural processes. Artificially high concentrations or combinations could be suspicious. A civilization might intentionally alter its climate or atmosphere, producing gases with no known biological or geological source. But alien industry need not copy human chemistry. A search can only target signatures that physics and engineering allow us to imagine. Solar panels have distinctive reflectance edges in laboratory materials. Large orbital structures could produce odd transit shapes. Spacecraft propulsion might generate spectral lines. Artificial illumination could alter phase curves. Most proposed signals lie beyond current sensitivity for Earth-level technology. They define what future telescopes could attempt. Technology may be easier to detect than biology in one sense. A beacon can be designed to be unmistakable. A narrowband radio signal containing a repeating mathematical pattern could eliminate many natural explanations. A powerful laser could be directed toward a known planet. Biology does not choose to announce itself. In another sense, technology is harder. A biosphere can persist for billions of years. A detectable technological phase may be brief. It may change frequency, become efficient, or intentionally hide. Earth has produced oxygen-rich air for hundreds of millions of years and strong radio technology for roughly a century. An observer arriving at a random moment would have a much larger window to detect biology. The searches should therefore continue in parallel. Atmospheric spectroscopy asks whether life changes planets. SETI asks whether intelligence changes electromagnetic or material environments. Neither assumes that the other must be common. The absence of confirmed signals after 6 decades sounds longer than it is. Radio astronomy has examined many stars, but often for minutes or hours. Frequency ranges are vast. Transmitters may point elsewhere. Civilizations may be separated by thousands of years. Earth has not maintained one all-sky beacon through even a human lifetime. A galaxy can contain technology and still appear silent under a sparse survey. At the same time, non-detections are becoming scientifically meaningful. Surveys can rule out continuously broadcasting transmitters above certain powers around selected stars. Infrared searches constrain the abundance of civilizations capturing most of a galaxy's starlight. Radio observations limit bright beacons in particular bands. The silence is being measured. It is not yet absolute. Perhaps the deepest SETI difficulty is deciding whom to expect. A technological species could be biological, machine-based, or a mixture. It could live on a surface, underground, in orbit, or among several stars. Its timescale could be slower or faster than ours. It may value communication or have no reason to transmit. Science cannot search every psychology. It searches physical consequences, energy use, information-bearing signals, atmospheric chemistry, orbital structures, motion inconsistent with gravity alone. The question changes from what would aliens do to what traces can technology not avoid, or what traces might it deliberately make universal. The hydrogen line was one early answer. Waste heat is another. No answer guarantees that anyone is listening from the other side. Listening raises the question of speaking. Should Earth transmit a deliberate message? Humanity has already released signals into space, but most ordinary broadcasts fade rapidly and are not aimed at particular stars. Powerful radar beams have traveled farther. Spacecraft communication leaves the solar system in narrow directions. A nearby civilization with sufficiently sensitive equipment could in principle detect some emissions if geometry and timing aligned. Deliberate interstellar messages are different. They concentrate power, choose a target, and encode information intended to be recognized. In 1974, the Arecibo radio telescope transmitted a short message toward the globular cluster Messier 13 during a ceremony marking an upgrade. The signal encoded numbers, chemical elements, a simplified structure of DNA, a human figure, the solar system, and the telescope. Messier 13 is about 25,000 light-years away and moves through space. The transmission was primarily a demonstration rather than a practical attempt at conversation. A reply could not return on any human historical timescale. The message also revealed the difficulty of universal language. Binary numbers may be recognized by a technological receiver. Prime numbers or simple geometric relationships can indicate intention. Physics provides shared constants, but diagrams depend on arrangement. Biology depends on local chemistry. Even the decision to send a picture assumes a receiver constructs space in a comparable way. Meaning must be built from common ground. The Pioneer plaques and Voyager golden records attempted a different form of communication. The Pioneer spacecraft carry engraved plates showing human figures, a map based on pulsars, and the spacecraft's path from the solar system. Voyager 1 and 2 carry records containing images, natural sounds, music, greetings, and scientific information. The spacecraft are moving through interstellar space, but the chance that another civilization will encounter them is extremely small. Their value is partly inward. Humanity created a portrait of Earth and placed it beyond the planets. The golden record does not prove confidence that someone will find it. It demonstrates that the question of company can change how a species describes itself. Active SETI, also called messaging extraterrestrial intelligence, remains debated. One position argues that detectable civilizations may already know Earth is a living planet from atmospheric oxygen and that modest transmissions add little risk. Another argues that no small group should make a decision representing the whole planet when consequences are unknown. The debate often imports human histories of contact, exploration, conflict, and inequality into situations where no evidence about alien motives exists. Risk cannot be calculated without probabilities. Silence cannot guarantee safety. Transmission cannot guarantee benefit. The scientific issue becomes an ethical and political one. Who speaks for Earth? What target is chosen? What is said? How long should a beacon continue? Would future generations agree? No international authority currently answers these questions for all humanity. Listening is passive in comparison, though even interpreting a signal would involve global consequences. Suppose a narrowband transmission arrived tomorrow and repeated from a nearby star. The first task would be verification. Other telescopes would observe independently. The signal's direction would be checked. Doppler drift would be compared with planetary motion. Human satellites, spacecraft, and interference would be excluded. Data would be released and argued over. Confirmation could take time. If the signal contains structured information, decoding might take much longer. A simple repeating pulse could prove technology without revealing language. A broadband transmission could contain data beyond our ability to identify. Compression makes meaningful information resemble noise unless the encoding is known. Encryption could make it indistinguishable from randomness. The first confirmed technosignature might reveal only that someone existed when the signal began its journey. If the source were 1,000 light-years away, the transmission would describe a civilization 1,000 years in its past. It might no longer exist. Any reply would reach that system 2,000 years after the moment we observed. Contact would begin as archaeology carried by light. The nearest stars shorten the delay, but not enough for ordinary conversation. A message to Proxima Centauri takes more than 4 years. A reply sent immediately creates a round trip of more than 8. To TRAPPIST-1, the round trip approaches a human lifetime. Distances do not make communication impossible. They change its social form. A civilization could send archives, science, art, or warnings without expecting dialogue. It could maintain beacons across centuries. A network of long-lived societies could exchange slowly. The assumption that communication must resemble a live conversation is another local habit. Physical travel is harder. The fastest human spacecraft would take tens of thousands of years to reach even the nearest star if directed there. Future propulsion concepts include nuclear fusion, antimatter, laser-driven light sails, and generation ships. Each faces engineering, energy, shielding, navigation, and reliability problems. Small robotic probes are more plausible than carrying biological communities. The breakthrough Starshot concept proposes accelerating gram-scale sails with powerful lasers to a significant fraction of light speed. A probe might reach Alpha Centauri in a few decades. It would need to survive acceleration, interstellar dust, and a high-speed passage, then return data across light years with tiny onboard power. The concept remains research, not an operating mission. A civilization much older than ours may have solved problems we have not. Physics still imposes distance and energy. No evidence shows that faster-than-light travel or traversable wormholes can be used for interstellar exploration. Speculation about visitors should not replace the standards applied to distant signals. An unidentified observation is not evidence of an extraterrestrial craft. It may reflect an aircraft, balloon, satellite, atmospheric effect, sensor artifact, or simply insufficient information. Demonstrating a visitor from another star would require evidence that the object is technological, non-human, and genuinely extraterrestrial. No publicly verified observation has met that standard. The absence of visiting spacecraft does not settle the Fermi question. Interstellar probes might be rare, tiny, slow, or never built. The productive scientific response is to define observations that could distinguish an artifact from ordinary objects rather than to treat mystery itself as proof. Technosignature science becomes strongest when it joins mainstream astronomy. A survey for unusual infrared objects can find dusty stars and galaxies even if no technology appears. A search for strange transits improves knowledge of debris disks and stellar variability. Radio SETI develops signal processing tools. Atmospheric pollution studies improve exoplanet chemistry. The search produces science during silence. This helps protect it from dependence on one extraordinary result. The same principle guided exoplanet detection. Before 1992, planet searches improved stellar measurements and instruments, even while finding nothing reliable. The methods matured until signals survived. Astrobiology may follow a similar path. False positives will be removed. Candidates will fail. The catalog of ordinary atmospheres will grow. Only then will an anomaly be understood as unusual against a population. One planet with oxygen is difficult to interpret. 100 planets reveal which gases occur without life. One red dwarf atmosphere is ambiguous. A survey across stellar activity and planet mass reveals patterns of atmospheric loss. One strange radio event is unresolved. Millions of star hours define what transmitters are absent. The search for company requires patience because the background must be learned before the exception can be recognized. Humanity is still learning the background. Most known exoplanets were discovered within 3 decades. Atmospheres of small temperate planets have only begun to be tested. The most powerful dedicated observatories remain future projects. SETI has searched a tiny fraction of possible directions, frequencies, times, and signal types. Silence at this stage is information without a verdict. The old philosophical question has become measurable, but the experiment is young. The next stage of the experiment is being built from several directions. Planet catalogs continue growing, but the goal is no longer only another count. Astronomers need a population with measured radii, masses, ages, stellar radiation, and atmospheric properties. A planet cannot be interpreted without its star. Stellar mass sets the orbit. Stellar radius sets the planetary radius inferred from transit depth. Ultraviolet radiation controls photochemistry. Flares drive escape. Age determines how long the planet has evolved. Small errors in the star become large errors in the world. Spectroscopic surveys, astrometry, and astroseismology improve stellar measurements. Astroseismology reads oscillations across a star's surface, much as seismic waves reveal Earth's interior. The frequencies constrain stellar density, age, and structure. The host star becomes part of the planetary instrument. NASA's Nancy Grace Roman Space Telescope is built to expand the exoplanet census through microlensing and direct imaging technology demonstrations. Its galactic bulge survey should find planets at wider orbital separations, including cold worlds and low-mass planets difficult for transit surveys. It may detect free-floating planets through brief lensing events. These discoveries will reveal how common solar system like outer regions are. A system with a temperate rocky planet can also contain giant planets that shape comets, stability, and formation. The architecture matters beyond the habitable orbit. European missions add complementary views. Plato is designed to search for transiting planets around bright stars and measure stellar ages, emphasizing longer-period terrestrial planets. Ariel is designed to survey the atmospheres of about 1,000 exoplanets, mostly warm and hot worlds. Those planets are not primary life targets, but their spectra will teach how atmospheres depend on size, temperature, formation, and stellar environment. Before recognizing an unusual habitable atmosphere, science needs to understand ordinary atmospheric diversity. Large ground observatories will collect more light and resolve finer spectral detail. Adaptive optics measures the distortion produced by Earth's atmosphere and changes mirror shapes rapidly to correct it. Coronagraphs suppress stars. High-resolution spectrographs separate planetary motion from stationary contamination. Nearby red dwarf planets may become accessible to combinations of direct imaging and spectroscopy. Earth-like planets around Sun, like stars, remain the harder goal. The Habitable Worlds Observatory is intended to search nearby stars directly. Its design must control starlight at extraordinary precision. A tiny wavefront error can scatter enough light to hide a planet. Mirrors, detectors, coronagraphs, and pointing systems must remain stable. The technical difficulty reflects the signal. Viewed from far away, Earth is a pale point beside a star 10 billion times brighter in visible light. All oceans, forests, deserts, clouds, cities, and living organisms are compressed into that point. A spectrum may separate water vapor, oxygen, ozone, methane, carbon dioxide, and surface reflection. Rotation could alter brightness as continents and oceans pass through view. Seasons could change gases or colors. Polarization could reveal clouds and oceans. No one measurement will reconstruct an exact globe. Together, they could establish that a small planet has liquid water conditions and atmospheric chemistry difficult to maintain without a biosphere. A future detection will need a scale of confidence. Scientists have proposed frameworks that move from initial signal to contextual assessment and independent confirmation. The first level may be a feature associated with biology. The next asks whether contamination or instrument error can explain it. Then whether abiotic chemistry can produce the abundance. Then whether the planet is actually habitable. Then whether another observatory repeats the result. A mature claim may involve several gases, planetary climate, stellar ultraviolet light, surface pressure, and models that predict the same spectrum. The language matters. Possible, tentative, suggestive, strong evidence, confirmed. These words should correspond to evidence, not excitement. The discovery of life would be socially immense, creating pressure to announce early. The K218b debate showed how quickly a possible molecule becomes a story about organisms. Future teams will need transparent data and independent analysis before public certainty. A false positive would not destroy astrobiology, but repeated overstatement could weaken trust. Caution does not remove wonder. It protects the discovery worth waiting for. Several forms of evidence could arrive, and they would not be equivalent. A microbe found beneath Mars, if truly indigenous, could show a second origin of life. But Mars and Earth exchanged rocks through impacts. Microorganisms or prebiotic material could in principle have traveled between them. If Martian life shared the same genetic code and cellular machinery, it might represent common ancestry rather than two origins. Life in Enceladus or Europa would be harder to connect through natural rock exchange, though not impossible to discuss across solar system history. A radically different biochemistry would provide strong evidence that life began independently. An exoplanet biosignature would be remote. No sample would enter a laboratory. The inference would depend on planetary scale chemistry. It could show a global biosphere without revealing cells, genetics, or complexity. A technosignature could be logically clearer. A repeating narrowband signal carrying structured information would have no plausible geological metabolism. It would establish technology and therefore life and intelligence in one observation after verification. Yet it might reveal less about biology than a microbial sample. The most dramatic evidence is not always the most complete. Suppose HWO eventually finds oxygen, methane, water, and a moderate climate on a nearby Earth-sized planet. The star is quiet. Models cannot sustain the gas mixture geologically. Another telescope confirms it. The world would become a leading inhabited candidate. Scientists would still ask whether unknown photochemistry or surface reactions could imitate the signal. The word confirmed might require years and a population of comparable planets. Suppose instead a probe flies through the plume of Enceladus and detects complex organic patterns, cell-like compartments, and isotope ratios associated with metabolism. Contamination controls would be examined. Abiotic synthesis would be tested. A return mission might be demanded. The closer evidence may be more chemically detailed but more vulnerable to contamination from the spacecraft. Suppose a radio telescope receives a signal of prime number pulses from a planet around a nearby star. Other observatories detect it. The frequency drifts exactly with the planet's orbit. The pattern repeats. The existence of technology could become certain before the message is understood. The discovery would arrive as mathematics without a face. Each scenario changes Are we alone? Differently. Microbial life would show that biology is not unique. An oxygenated exoplanet would show that biospheres can alter other worlds. A technosignature would show that evolution has produced another system capable of inquiry or engineering. More than one discovery would begin comparative biology. With two biospheres, scientists could ask which chemistry is universal and which is local. Do both use carbon? Do both use liquid water? Do both store information in linear polymers? Do both build cells? Do both evolve through variation and selection? One alien organism could turn biology from the study of one lineage into a cosmic science. The absence of discovery also teaches. If dozens of truly Earth-like planets are characterized and none shows a biosignature, the probability of detectable biospheres would fall. If hundreds are observed, the constraint becomes stronger. A null survey cannot prove Earth unique because life may be hidden or produce unfamiliar gases. It can show that modern Earth-like atmospheres are uncommon under the sampled conditions. If SETI surveys millions of nearby stars with sensitivity to powerful continuous beacons and finds none, those beacons become rare. Other technologies remain possible. Science replaces unlimited speculation with bounded possibilities. This is the quiet power of a census. One unusual world can dominate imagination. A population reveals frequency. Exoplanet science has already performed this transformation once. Before 1995, planetary systems were speculative. After thousands of detections, they became normal. The next transformation may concern atmospheres. Perhaps most small planets around red dwarfs are bare. Perhaps many retain air. Perhaps water worlds dominate. Perhaps Earth-like mixtures are rare. Perhaps biological disequilibrium appears more than once. We do not know because the atmospheric census has barely begun. There is another observational limit that receives less attention. Earth's biosphere is detectable partly because sunlight illuminates it and the atmosphere is exposed. Life inside an icy moon may be abundant, yet invisible from interstellar distance. A civilization using low energy may leave little trace. A planet beneath global haze may hide surface chemistry. The universe could contain life that astronomy cannot count. Any estimate from detection must include detectability. The observed fraction is not always the true fraction. Astronomers understand this from planets. Most planetary systems were once invisible because instruments lacked precision. The planets existed before their signals became measurable. Life elsewhere, if present, does not begin when a telescope detects it. Our catalog may be empty because the biospheres are absent, because they are quiet, or because the instrument is not ready. The difference is the work of the next generation. The search also changes how Earth is seen. In December 1990, a spacecraft on its way to Jupiter returned briefly to the planet from which it had been launched. Galileo needed Earth's gravity to alter its trajectory. During the flyby, Carl Sagan and a small team persuaded the mission to use its instruments in an unusual experiment. They would pretend not to know that Earth was inhabited. The question was not whether the spacecraft could photograph a city from nearby. The question was whether the measurements available to a planetary probe could build a scientific case for life without beginning from the answer. Earth became a control experiment for astrobiology. Galileo measured the atmosphere, surface, radio environment, and reflected sunlight. The results were published in 1993 under a deliberately simple title, A Search for Life on Earth from the Galileo Spacecraft. The experiment found abundant molecular oxygen. Oxygen alone was suggestive rather than decisive. Under some conditions, non-biological processes can produce it. But Earth's atmosphere also contained methane far from chemical equilibrium with oxygen. The gases should react and decline unless processes continued replenishing them. The spacecraft detected a broad surface pigment with a sharp change in reflectance near the red part of the visible spectrum. Vegetation absorbs visible light for photosynthesis and reflects more strongly at longer wavelengths. From orbit, the effect appeared not as an image of a leaf, but as a planetary spectral edge. Galileo also detected narrowband, pulsed, amplitude-modulated radio emission. That signal was unlike any ordinary geological or meteorological process. It was evidence not merely of biology, but of technology. The experiment succeeded. It also revealed how incomplete a successful detection could be. High-resolution images obtained during the flyby did not simply present human civilization as an obvious global pattern. Clouds hid the surface. Large regions contained ocean, ice, desert, and vegetation. The planet's inhabitants remained mostly invisible as individuals. The strongest evidence came from collective effects. Billions of organisms altered atmospheric chemistry. Vegetation changed reflected light across continents. Technology placed structured electromagnetic signals into the environment. No tree, whale, city, or person needed to be resolved. Life became visible through what the whole planet did. Galileo observed Earth from nearby, not from another star. Its instruments and geometry were different from those of a future exoplanet telescope. Yet the logic of the experiment became foundational. Look for several independent clues. Place each clue in environmental context. Do not require one molecule to carry the entire conclusion. Ask whether the planet is easier to explain as living than as lifeless. Earth is the only place where that test can be performed while the correct answer is known. It also shows how easily a living world could be misunderstood. A distant observer might detect oxygen and infer photosynthesis without knowing forests, plankton, or cyanobacteria. It might detect methane without identifying wetlands, microbes, agriculture, or animals. It might see changing cloud patterns and miss the continents beneath them. At another time in Earth's history, the same observer could reach a different conclusion. For much of the planet's inhabited past, atmospheric oxygen was low. Land plants did not yet exist. Technology occupied only the most recent instant. A telescope selecting Earth at random from the last 4 billion years would usually not see the modern combination of oxygen-rich air, vegetation, and radio emission. A planet can be alive without looking like Earth today. It can also look chemically interesting without being alive. That is why an exoplanet spectrum needs history, atmosphere, star, surface, and statistics around it. From the distance of another star, Earth would be an unresolved point beside a source about 10 billion times brighter in visible light. Clouds would dominate much of the reflected signal. Oceans, continents, ice, vegetation, dust, and atmosphere would blend together. Rotation would change the brightness. Seasons would alter the pattern. The planet would carry information without offering a map. The information would also be old. A telescope 100 light-years away sees Earth 100 years in the past. At 1,000 light-years, it sees the planet before modern radio astronomy. At 66 million light-years, if an impossibly powerful telescope could resolve Earth at all, the light arriving now would have left during the final age of non-avian dinosaurs. There is no single present visible across the universe. Every world answers from another date. Proxima Centauri appears as it was just over 4 years ago. TRAPPIST-1 appears roughly 40 years in its past. K2-18b appears more than a century in its past. A signal crossing the galaxy may describe a civilization that has changed or vanished before the message reaches Earth. A planet that looks lifeless in our telescope may develop life long after the light we are receiving began its journey. The galaxy does not conduct one simultaneous roll call. It offers a mosaic of different times. This delay makes the silence harder to interpret, but it does not make observation meaningless. Hydrogen absorbs the same wavelengths. Gravity produces repeatable orbits. Water follows the same physical relationships among temperature and pressure. A real radio source follows celestial motion. An atmospheric model must conserve matter and energy. Life elsewhere may be unfamiliar, but it cannot ignore physics. The search is therefore a sequence of measurements rather than a choice between optimism and pessimism. A stellar wobble, a transit, a radius, a mass, a density, a temperature, an atmosphere, a chemical imbalance, a repeated signal. Each level narrows the next. Skipping levels creates a story more quickly than evidence can support it. The history of exoplanets repeatedly rewarded patience. False planets around Barnard's star improved the understanding of instrumental error. The hot Jupiter 51 Pegasi B forced migration into planet formation. Kepler revealed common small worlds and the biases of detection. TRAPPIST-1 showed that Earth size does not mean Earth-like. K2-18b showed that a possible molecular feature must survive different pipelines and broader chemistry before it can become a claim about life. The Galileo experiment showed what a strong case might eventually resemble. Not one dramatic sign. Several clues that agree. The current search has not yet reached that standard beyond Earth. More than 6,000 confirmed planets are a beginning rather than a representative atmospheric census. Only a small number of temperate rocky worlds are accessible to present spectroscopy. No observatory has examined a large sample of true Earth analogs around Sun-like stars. SETI has listened deeply in selected directions and frequencies, but not continuously across every nearby system and every possible signal. Europa Clipper can assess habitability, but it will not sample Europa's ocean for cells. No mission has yet flown through Enceladus's plume with a complete life detection laboratory. The experiment remains unfinished. This statement is different from assuming that the universe is crowded. Large numbers of planets do not guarantee life when the probability of its origin is unknown. It is also different from assuming that Earth is alone. A sparse search cannot turn silence into proof of absence. The accurate answer remains between those intuitions. We do not know. That answer contains less drama than a discovered civilization and more scientific value than an unsupported conclusion. It identifies exactly what evidence is missing. If life is found independently on Mars, Europa, or Enceladus, biology will no longer rest on one origin. If a distant atmosphere shows a durable pattern that geology cannot sustain, biospheres will become part of comparative planetary science. If a structured signal arrives from another star, technology will be known as a second cosmic outcome. If future surveys examine many suitable worlds and find none, rarity itself will become measurable. Every result changes the question. The work may extend across generations. The astronomers who searched Barnard's star did not know that Kepler would count planetary populations. The designers of Kepler did not know which atmospheres Webb would debate. Cassini collected particles from Enceladus years before archived data revealed phosphorus. A telescope can gather light whose most important interpretation arrives decades later. Data survive the observer. The Habitable Worlds Observatory, if built and launched, will be used by scientists whose careers are only beginning. A suspicious spectrum may require another mission not yet designed. The question is older than scientific astronomy and may outlast several generations of instruments. No one listening tonight needs to solve its missing probabilities. The uncertainty belongs to the evidence still traveling through space. The distant transit from the beginning can now return. A planet crosses its star. Perhaps it is a small rocky world around a red dwarf. Perhaps a larger world with a hydrogen atmosphere. Perhaps a planet not yet named in any catalog. The star's light reaches the top of the atmosphere. Some rays pass above it. Some enter. A photon encounters a water molecule and is absorbed. Another passes through methane. Others scatter from haze or cloud. Most travel onward. The planet moves across the star and away. The altered light continues through interstellar space. Dust may remove a small fraction. Gravity may bend its route slightly. Years pass without any event experienced by the light itself. Eventually, the wave reaches a telescope. A mirror collects what would otherwise continue past Earth. The light is reflected toward instruments, divided by wavelength, and converted into electrical measurements. The spectrum enters a computer. Calibration removes detector behavior. Stellar models are applied. Several transits are combined. A line or band begins to appear. At first, it is only a difference smaller than ordinary human senses could notice. A team checks the pipeline. Another team uses a different one. The feature changes. More observations arrive. Perhaps it disappears. Then the planet becomes scientifically quieter and the methods become better. Perhaps it remains. Another molecule appears. The atmospheric temperature is constrained. Clouds are measured. The star's ultraviolet radiation is known. Geological models fail to sustain the chemistry. A second observatory confirms it. The possibility of life strengthens through years of resistance. This imagined sequence has no guaranteed ending. The missing wavelengths may belong to water on a lifeless planet. They may belong to methane made in rock. They may be a star spot. They may be noise. Or one day, after every ordinary explanation has been tested, they may belong to a living world. The first evidence may not reveal oceans or organisms. It may be a pattern in starlight. Humanity will compare it with Earth, with laboratory chemistry, with Mars, Venus, and ocean moons. Papers will disagree. Telescopes will return. The word life will be used carefully and then, perhaps, with confidence. Until that day, the search itself has already answered several smaller questions. Planets are not rare exceptions. Nature builds worlds and forms the solar system did not predict. Some rocky planets occupy temperate orbits. Atmospheres can now be measured across interstellar distance. The ingredients of organic chemistry occur in space. Water and chemical energy exist on several worlds close to home. Technology can listen beyond its own star. The largest question remains: are we alone? The scientifically accurate answer tonight is that no confirmed evidence has shown otherwise, and no adequate survey has shown that we are. The universe has not answered yes. It has not answered no. It has given us light carrying incomplete information and minds capable of learning how to read it. That can be enough for this moment. The catalog can continue growing without being counted now. The distant planets can continue their orbits without being imagined one by one. Red dwarfs can flare. Ocean moons can move beneath ice. Radio telescopes can listen through quiet frequencies. Future mirrors can remain unfinished. The question does not need to stay active in attention. Somewhere, starlight is crossing an atmosphere. Somewhere else, it is traveling through darkness. Here, the room can remain still while the Earth turns beneath the stars. No signal requires an answer tonight. No spectrum needs to be interpreted before morning. The unknown can remain unknown without becoming threatening. It is simply distance, time, chemistry, and possibility waiting beyond the reach of present instruments. The light will continue. The search will continue. For now, attention can loosen from the stars and return to the quiet nearby world that is known to be alive. Sleep well. Good night.